right, now that we have actually studied the impedance and the admittance Smith charts, I would like to give you a numerical example that we can use both of those charts at the same time, and hopefully that will help you manage how do you move along the Smith chart when you have to add impedances and admittances. This is something that takes some practice, so I do like to invite you to actually follow this video, and I would like to invite you to change that circuit example, the example circuit I'm giving you here, and make simple changes back and forth, and repeat this over and over again until you can actually get quite comfortable following and doing the operations you will see right here. All right, so what do we have here? We have a load whose normalized value is 1 plus j. Then right in parallel with this load, I'm adding an inductance. And the inductance, of course, has a negative part here of negative j, 0.5. And then there is also a series inductance. There's a second inductance whose now reactance is j 1.2. And what I would like to do is find out what is the input impedance right here. Now, once again, you can go ahead, of course, and do this calculation using your little calculator, but it's a lot more instructive to do it on the Smith chart and see what you get and understand how the impedances are moving and by how far they're moving. And so you can start building intuition of what are these inductors doing. Now, I'm going to use the ZY Smith chart right here. And so let's first of all go ahead and locate the load on the Smith chart. The load is given with its impedance, so I'm going to be using the impedance Smith chart, which is the red lines right here. So the load has a real part of 1, and it has an imaginary part of 1 as well. So here is the circle with a real part of 1, and here's the circle with an imaginary part of 1. And of course, at the intersection of these two circles, I will get my load. So here's my ZL 1 plus J1. Now, the beauty of this double Smith chart is that you can go ahead now and read the YL, the admittance of this load as well. Why? Because I can use now the blue circles, and if I use the blue circles, I'll find out that I have to read basically this circle right here, whose real part is 0.5, and then I will have to get this circle right here, whose value is 0.5. Now, of course, now I'm reading essentially the Y Smith chart, and I'm on the upper half, and therefore my value will be 0.5 minus j.5. So the point is, you don't have to make any rotations here. You just put the load down, and you look at the red circles to read the impedance, the Z part, and you look at the blue circles to read the admittance, the Y part. All right. Now I'm adding this inductance here, Y inductance 1. And it's much easier to work with admittances because the two loads here are in parallel. So I start with 0.5 minus j.5, and I have to add another negative j.5. So the real part of this thing will remain the same, but the imaginary part will become negative 1. So now I have to move along this circle right here, while the real part will remain the same, but the imaginary part will grow to negative j1. So here's the circle of negative j1. So that means that my point will be right here. So yx, which is the admittance of this right here, is going to be equal to 0.5 minus j1. And once again, by using the Smith chart now and by looking at the red circles, I can go ahead and read the real part as well. I'm sorry, the impedance part as well. So the real part is going to be on this circle here, whose value is basically 0.4. So you can see that my real part is equal to 0.4. And the imaginary part is going to be on this circle here, whose value is basically 0.8. Here's the circle. And that means that your imaginary part is plus j.8. So this is the first part. This is basically finding what's happening when I take my load and I add this inductance in parallel. Now, I have to add now my second inductance. My second inductance is in series. So I'm not going to be working with admittances. I'm going to be working with impedances. So I'm going to take the impedance of 0.4 plus j0.8, and I need to add j1.2 to this value. So adding j1.2 to this value will make the imaginary part equal to j2. So what I have to do is keep my real part constant. So I have to move along this circle here with a real part of 0.4 constant and move far enough until I hit this circle right here that basically has an imaginary part of 2. So that means that my ending point, my Z in, if you will have a 0.4 plus j2 impedance part. And of course, if you want to find the admittance, the Y part, you can simply read it from the Smith chart as we did before. You're actually on the circle of 0.1, which is this circle right here. So the real part is going to be equal to 0.1, and the imaginary part is slightly less than negative j0.5. And so the imaginary part is going to be equal to negative j0.48. And basically, that concludes the solution of this problem. So again, the important part here is for you to be able to practice. So practice as much as you can with this type of simple problems so you can feel comfortable managing both series components as well as shunt components. In series components, you're adding impedances. In shunt components, you're adding the admittances. So thank you. See you next time.